Okay, bounded area, that just means gross area. So we talked about how when we calculate area using definite integrals, we consider area above the x-axis. It's always calculated by the first fundamental theorem as being positive, and area below the x-axis is calculated by the first fundamental theorem as negative, okay, which is fine. A lot of times that's usually what we want. Like if we're doing, I always go back to the example of calculating work, right? If we're calculating work, computing work in physics, well, yeah, there's going to be positive work that's done and negative work that's done, and we need to account for both, right? And I think I've probably talked about this before, but like if I throw a ball up in the air, when it's in my hand and I'm accelerating it upward, I'm doing positive work on it, right? Because the application of force is in the same direction as the displacement. Well, when I catch the ball, I'm doing negative work because now I'm applying force opposite the direction of the displacement, right? And so we need to, generally, that's what we want. But there are times when we want to do something different, when we want to just calculate all of the area as positive. We could call that kind of gross area. So net area is normal. Gross area would be where everything is. Think of it as if you were going to cut a shape out of cardboard, you know, what would the area be of the cardboard that illustrates the area above the curve and below the curve, but thinking of it all as just positive area. That would be a situation, we'd want to do that maybe if we were talking about like total distance traveled in a car instead of calculating displacement, okay? Because I mean, even when you're, like if you say I'm going to go for a run, you don't say I'm going to go for a 0-mile run if I run out 3 miles and run back 3 miles, right? You say you're going for a 6-mile run. So we want to calculate distance traveled, not displacement. So there are definitely applications where we need to do that as well, right? So, okay, so let's look at one like this. Let's do two things. Let's find the net area and the area bounded of the bounded region. When we talk about a bounded region, that means gross area. So that means, you know, the part that's bounded above and below by a curve. Okay, so we always make this association. Make a note of that. So that's gross area. Well, the net area is easy, right? I mean, we won't even have to calculate. Let's just set the integral up at least. And you guys, I mean, it's not hard to calculate these integrals. But the net area here would just be what? So for this part, integral of what? From where to where? Four cosine x dx from, that's it. That's it, right? That's going to give me the net area where there's some cancellation between positive and negative, okay? Now, how am I going to calculate the area of the bounded region then, though? I know I mentioned this, but we haven't really done this yet. It's been a little while. What would I have to do? If I want to calculate.
So why wouldn't that give you the bounded?
This is giving me, here, I'll show you what this does. Let me just illustrate this. So if I go into Math Excel, not Math Excel, if I go into Desmos and I graph this function, there's the function, right? And here's the interval in question, right? So I'm going to get some positive area and I'm going to get some negative area. And it looks to me like that positive area there and that negative area there are going to cancel completely, aren't they? So the net area is just going to be, everybody get what I'm saying? We're going to have, like if I were to shade this in. Let me take a picture. right? So there's the area under the curve. I've got all this. What's that doing? That's not what I want to do. I want to do this. That's what I want. So this area right here is positive, right? And this area down here is negative. And because of the symmetry of that curve, those are going to be offsetting, aren't they? Those are going to cancel. So all I'm left with then is just this area over here. Agreed? Those would cancel out. So it would be the same thing as the area from negative pi halves to 0 would give me is going to give me the same area as from negative pi halves to pi. And I can show you that. If we go to Desmos, and if you haven't seen this, this is pretty cool that Desmos can do this. You can't calculate antiderivatives, but you can calculate definite integrals. So I can do, by just typing int, or you can get it from the menu down below from the keyboard, I can do a definite integral of, I've already defined f of x. Whoops, I do my limits first. So if I go from negative pi halves up to pi of f of x dx tells me it's 4. Okay, I guarantee if I do the same integral from negative pi halves to 0, I'm going to get 4. That's net area. Okay, everybody see that? Okay, now how could I go about calculating gross area here? What would I have to do if I want to calculate the bounded area? So the entire area, considering everything is positive, what would I have to do? Okay, I could, you're right, because I have the benefit of being able to see the graph here, right? But what if I couldn't see the graph? What's a more general strategy for this? Okay, so take this as positive, you're saying, right? Okay, how do I go about doing that? And first of all, okay, so there's an important point here, though. There's a cutoff point. How do I know the intervals that are going to define where the function has positive valued area and negative valued area? How would I determine, because I've got to set up those limits of integration, right? In this case, what you're suggesting is I'd take an integral from negative pi halves to positive pi halves, right? And then separately, I'll take another integral from pi halves to pi, right? But why? How do I know pi halves is the value I want to choose in between the endpoints? What's significant about that? There's nothing really profound here. I just want you guys to say it. Yeah, it's a 0, right? Okay. So I've got to define my integrals, separate integrals for the parts of the domain between all of the zeros, right? And then, of course, the endpoints of my interval, right? I'm going to start at the left endpoint of my total interval and end at the right point of my total interval. But any intermediate zeros, those have to be places where I'm stopping and restarting the integration process. Everybody get that? Okay. So if I've got one internal 0, then that means I'm going to have 2 integrals. If I had 3 internal zeros, I'm going to have 4, right? Does that make sense? Okay. If I have a 0 that's at an endpoint, that's not an internal 0. That's an endpoint anyway, right? We don't need to worry about that 0. Okay, so we got that part. So we know that we have to find the internal zeros, right, in our interval for our function, and set those up as boundaries of my integration. Okay, so now how do something else here, another issue. We want to calculate this area as positive and this area as positive. How do I accomplish that? There's more than one way to do this. I've got a personal bias here, I think is the easiest way, but see what I'm saying here? How do I know? The suggestion is this one we don't have to do anything to because it's already positive, right? This one, though, if I just apply the fundamental theorem, I'm going to get a negative answer. How am I going to ensure that that's positive? What could we do? Say it again. Of the negative, so I could put a negative out front? Is that what you're saying? That's one thing you could do. Sure, you could. What else? Why not? That's what I do. I just take an absolute value, and I indiscriminately take an absolute value of every part because it's never going to hurt you, right? Even if it's already positive, well, if I take an absolute value of a positive answer, it's just positive, no big deal, right? So once you break it up, just take take absolute values of each of those definite integrals. And then the other thing, and I think our book, what they do is they reverse the limits of integration, right? So if I want to make a -1 positive, instead of going from pi halves to pi, I would just go from pi to pi halves. Because if I go backwards, that's going to calculate area negative. If it's below the x-axis, it's negative. Negative times negative is positive. That seems cumbersome to me, personally. I think absolute value is just the way to go. It's just easier, right? So then what we would do here is we'd have to find on our, and we've seen the graph, right? So we already got 4 for that, right? What's the answer going to be for this one then, obviously? It's going to be 12, isn't it, right? Because we've seen the graph, so we know it's got to be 12. But if we're going from negative pi halves to pi, and this is our function, well, we know that there's our 0, right? So my bounded area then is just going to equal the absolute value of the integral of f of x from negative pi halves to pi halves plus the absolute value of the integral of 4 cosine x dx from pi halves to pi. That's it. Okay? Make sense? All right. Have at it. You guys are good. Okay, flip-flop.